So in this video, we're going to go over the periodic table. So what is the periodic table? The periodic table is just the table that has all of the elements on it. So it's just a chart with all the elements. But it's not just that. It's the chart with all of the elements that tells you about those elements. So it tells you about the properties of the elements given their location. So that is the purpose of this video. We're going to figure out why and how it tells you about the properties and then how you can use that. Because, I mean, we could have just made the periodic table look like this and just put all the elements in a list going down the table, right? But that wouldn't really tell us about all of those elements, like how they interact with other elements. That's what the periodic table tells us. So before we get into the periodic table, we need to discuss how elements work, how an element has a certain property. So if you recall, an element's determined by the number of protons. And the number of protons is going to determine the number of electrons in the ground state. Because protons and electrons in the ground state like to be equal to one another, so that the net charge is zero. But what is it that gives an element its properties? Is the proton what gives it its properties? That is not the case because the proton is all the way here in the middle. It is the electron that gives it its properties because the electron is floating around all the way out here. Not only that, it's also really small. So it is going to much more easily interact with other things. Maybe it pops off, maybe an electron hops on. That's going to be the main driver of the element interacting with the other elements and how the element typically interacts. So that is really going to give it its properties. So let's talk about these electrons a little bit more. How are electrons partitioned around an atom? Electrons don't just randomly float around the nucleus. It's not like you have the nucleus here and the electron's just doing its thing floating around. Instead, we have what's known as a shell. Basically, electrons are going to occupy discrete shells around the nucleus. So there's going to be some electrons here and some electrons here, but there's not going to be an electron, say, right there. They are rather confined to these discrete shells around the nucleus. You have the nucleus here, this is shell 1, this is shell 2, and they keep going. You have shell 3, and then you have shell 4, etc. So let's talk about these shells. The shells are always filled middle to outside. So if you had 10 protons in a nucleus, let's make its first shell and its second shell. It'll have these two shells, and it keeps having shells. It has infinite shells, really. We know there's going to be 10 electrons in this atom because we want protons plus electrons to equal 0, right? Or I should say protons minus electrons equals 0. The charge of the protons plus the charge of the electron should equal 0. So the electrons are going to be maybe hanging out here. And let's draw all 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they're ready to go. They're ready to go into this atom here. They're not just going to plop right into this far out shell. They're not going to do that because they want to be as close to this positive charge here as possible. So they're actually going to start out by going into the very middle shell. They want to be as close as possible. So they're going to go to this first shell first. They're going to go here. But how many can go here? That's the question. Because they want to be close to the positive charge. They like the positive charge. But remember, electrons repel one another. So they don't want to be near one another. It turns out that the first shell can hold up to 2 electrons before they start repelling each other too much to all occupy that shell. So next, they're going to start filling the next available shell, and that's this shell 2 here. And they're just going to go and populate this shell. And as it turns out, up to 8 electrons can populate that second shell. So the first shell can hold 2 electrons, the second shell can hold 8 electrons. So let's draw that 10 protons in the middle, and then you have 1, 2 electrons in the first shell, and then 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second shell. And this is a proper configuration. So let's talk about these shells a little bit. Well, we know that protons like to equal electrons. But another note about these shells is these shells like to be full. So if we had, say, a nucleus here with 2 electrons, and then this one had 1, 2, 3, 4, 5, 6, 7, we know this can hold up to 8, up to 8. It's actually stable for it to have those 8. It likes having 8 more than it likes having 7. So now we know that protons like to equal electrons and that shells like to be full. And since we know that the innermost shell is always going to be full, as long as shells farther out are being filled, because you're going to fill the inner shell before you move to the outer shells, then we can clarify this to say that elements are going to tend to have their valence shells full, valence shells filled up. So that is a major property of elements. There are two main ways that they're going to accomplish having their valence shells full. The first way is kind of the more common. So take two hydrogen atoms. You'll have a positive charge here and then an electron floating around it. And then you'll have a positive charge here and it'll have an electron floating around it. The primary way, the most common way that they're going to have their outer valence shell full is if these electrons go ahead and are shared amongst the two elements. So now you'll have, should redraw this, now you'll have this hydrogen and this hydrogen, and they'll actually be sharing their two electrons amongst themselves. And what does this accomplish? Well, if you see, this system, this like unit, this molecule, has 2 protons and 2 electrons in total. So we know that protons does indeed equal electrons in total. So we know that it's stable on that front. The second reason that it's stable is now both of these have full shells. They're sharing, but they're still full. So that makes it relatively stable. It makes it nice and stable. The second way that you can have a shell get filled up is through ionization. And as we discussed earlier, we said that if an electron pops onto an element and then turns that element negative, or if an element loses an electron and then turns positive, that's an ion. Those are ions. Well, we didn't really discuss why that might happen. This is why that might happen. Because they want to have their valence shell full. So they can accomplish it in 2 ways. If you had, say, let's take a proton and it's got just this electron. This is a hydrogen. It could find a partner to bond with, which it does a lot. But it could also just say, I'm just going to get rid of this electron and give it to somebody. So maybe you have something that really likes electrons over here, and it's just going to yank that electron right off, and it's going to make this electron over here now. And now it doesn't really have its valence shell full, so to say, valence shell full, because now it doesn't have any valence shells, but that's also stable. Because technically, in all instances, it always has all of these shells around it and they're all empty. So really an empty or a full shell is stable. Both of those are actually stable. The second way is grabbing an electron. So maybe you have your nucleus, and this just has a number of protons. We won't put them all there. And you have an electron in this shell, and then this shell is almost full. 3, 4, 5, 6, 7. And there's an electron hanging out over here. This one might just go ahead and instead of going and finding something to share with, it's just going to grab this electron. And now it's going to have its valence shell full. So both of those ways do end up making it either negative or positive. But depending on the atom that you're talking about, sometimes that is actually more stable. So even though it doesn't have protons equaling electrons, it has that valence shell, valence full property or empty property, which is also stable. So let's talk about the periodic table a little bit more now that we have that insight. So I've drawn a little periodic table here, and let's just go through it and see what this might be able to tell us. So how the periodic table works is that you're going to read like you're reading a book. So you'll read in general, at least, left to right and top to bottom. So left to right, top to bottom. And every time you move over, you're just going to add a proton. So this would be corresponding to the first proton, and this to two protons, this to three protons, etc. So let's think about it. This would be hydrogen, and it'll have one proton and one electron in its ground state. So let's just draw that up in this corner. Proton, and then it has one electron in that shell. This, moving to there, is helium, which is going to have two protons and two electrons, sorry. So let's draw that in the top right, and that corresponds to this helium over here. This right here is lithium, and that's going to have three protons and three electrons. So it'll have proton, 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 and one, two in the first shell, and then this one in the next farthest shell. And then this is going to have the same as that, just with another one. And we're going to skip a couple so that we can loop back to this next one down so I can show you what I'm really talking about here. So if this has lithium has three, then this, or I'm sorry, lithium has three, and then this boron or beryllium will have four, got ahead of myself, and this boron will have five, carbon six, and then this nitrogen will have seven, and then you have oxygen at eight, and then you have fluorine at nine, and you have neon at 10. Now, this right here is going to be sodium, and it's going to have 11. Now, let's think about what it would look like if it had 11. You'd have 11 protons in the middle, and then its first shell would have two, and that'll be full. And then its second shell will have eight, which will also be full. That's up to 10. And now its third shell is going to be having one electron in it. So now we have what the first three in this column here look like. You have your hydrogen, which has one proton and one electron. And then you have your lithium, which has three protons, and the first shell filled for the second one to have one electron. And then you have your sodium, which is going to have 10 protons, so that its first and second shell are full, and its third shell has one electron. So what do you notice here? What you should notice is that all three of these have the same outside valence configuration. Their valence shells have the same number of electrons. And since we already talked about how the electrons are going to be determining how it reacts with things, and the valence shells in particular like to be full, the outer shells like to be full, we can probably see how having one electron in your outermost valence shell might make you act in a similar way as another element who also has one electron in their outermost valence shell. And that is what the periodic table is doing. All of these columns you see refer to atoms, or elements rather, with the same number of valence electrons. So if you see them in this column, they have the same number of valence electrons. And that can tell you a lot about how it's going to interact with things. And as we'll see, as this goes on, is that that's not the whole picture. Actually, the periodic table is a little bit better than that. It not only tells us that, it also tells us stuff about what are known as orbitals, which is a quantum mechanical property of the atom. And those are also insightful. But I'm going to leave that for a later date. For now, it's important to just know that each column is referring to similar valence characteristics. And as we know, those valence electrons are going to be determining how it interacts with things in general.